Okay, well, this is a bonus video I just decided to make to see how this goes. I've shown you already a stochastic gradient descent, but I told you in class that you can do a gradient descent that's not stochastic if you just recalculate things for every training set point at each step, right? So if you have tens of thousands of training set points, then this is going to be computationally very expensive. And so stochastic gradient descent is really good for that. But with the example we're doing, we don't have that many training set points. So we should be able to do a regular gradient descent with no randomness on the whole set at each step. And Excel's not very good at this. It's kind of a pain to set up in Excel. I've set it up here. I'm going to show you what I did. But just so you can see this gradient descent idea working in practice again. Then I'll show you how it compares to the results we got when we did the stochastic gradient descent. So the first thing to note is I set up all the X's and Y's and stuff horizontally instead of vertically. So this is like the transpose of the way we had it on those first sheets, right? We had the X1, X2 like this in columns. Now they're rows. And the Z, and so then I have my thetas over here. Thetas are over here. Time, eta, and lambda are over here as well. Okay, so those are the same as the other video. Obviously, if you haven't watched the other video, please watch that one first. Otherwise, nothing I say is going to make any sense. All right, so then I calculate based on the x, y, and z, the x's and the y's, and the thetas. I calculate the z, and I calculate the loss. These are essentially the same as before. The formulas are a little bit different with dollar signs in different places just because of how I had to copy and paste it over. What you need to make static to get it to copy and paste well. You can look at this for reference. You can figure it out if you want. I also want to mention, again, this is a bonus video, right? This is not something you're expected to know on your midterm or anything, but just if you want to see how gradient descent works without the stochastic element, where we are calculating every point at each step, this is how we would do it. So we have our Z and we have our loss for every point in our training set. And then what we're going to do is we're going to do the updates. Now, just because I think it's a little bit easier, I've broken it down into the part of the update that is based on loss and the part of the update that is not based on loss, that's just based on regularization. Oops, I realized I did something a little bit wrong here, but I'm just going to fix it. That's okay. So anyway, it's fine. So the loss updates, how do they go? Well, they just say if, and I'm updating theta 1 and theta 2 and theta 0 at each point if there's a loss. I'm going to have, see, and this is just like with the perceptron, right? So if there was no loss, we would not update. Otherwise, how would we update? We would update based on y times x1 for theta 1. Or we would update based on y times x2 for theta 2, or based on just y for theta 3. Now you notice that in perceptron, I did theta 1 plus y times x1, and theta 2 plus y times x2, and theta 3 plus y. I'm not doing that part yet because I need to average these out first. So I'm just doing the y times x1, or the y times x2, or the y part of this. Okay, so I just find that for each point. These are the things that we would add to theta 1, theta 2, and theta 0 in perceptron if there was loss, right? If there's no loss, these should all be zeros. And we can see like in the second step, hey, these are all zeros for these points because there's no loss at these points. All right, so we do that for every point. And then in order to calculate the actual update we make to theta, we average these updates. And that's because if we look in the objective function, the loss function for the whole thing is just the average, the mean of the losses at the individual points. And so when we take the derivative, because losses are just like, add them all up and divide by n, we're going to just add up all the updates and divide by n. So if we do the average of these updates, and you can see this is what I've done here, this is the average of this row, this is the average of that row, and this is the average of that row, then we're going to know how to update thetas based on loss. We also have a regularization part, right? For the regularization, it's just going to be lambda times, we're going to take the theta 1 and we're going to subtract lambda times theta 1, right? So I put minus lambda times theta 1 here and minus lambda times theta 2 here. And then for theta 0, it's 0. We don't update theta 0 for regularization, right? For regularization, we're only updating theta 1 and theta 2. So then the overall update, what we're doing is we're doing the loss update plus the regularization update, and we're multiplying by eta. Remember, we need to multiply by eta in order to make this all converge, right? And so then what I did was I just copied and pasted this whole thing down again, right? But of course, if I copy and paste this down, I need to change certain things. So what's happening here? What do I actually change to make this work? So eta, so the eta is already 1 over 1 plus time. I already have that coded. The lambda is just fixed. Lambda doesn't change. Time, this should just be the previous time plus 1. And you can see doing that will change my eta, which will change my regularizations, and so on. What should the thetas be? The new theta should be the previous theta plus this overall update I got. And then the same thing for theta 2 should be the old theta 2 plus the update for theta 2. And the old theta 0 should be the old theta 0 plus the update for theta 0. Right? And so with those changes, now my thetas are updating, and my etas are updating, my time is updating, which means that all of this stuff will change, and we should get some good stuff happening here. Now I'm going to copy and paste this all the way down. Each block here is taking up 8 rows, so I'm copying and pasting all the way down to row 800 in order to get 100 iterations. And so when I do this, I'm getting eventually I'm getting this, which now is my equation of my line after all those updates. And we can compare this to what we got when we did it with the random points, the stochastic points, and it's a different line. You can see it's different. I also have over here another random set of points. I slightly tweaked this sheet. And the way I tweaked the sheet is I made the first 3 points random as well. Because here's the thing about this stochastic stuff is that because the eta is always shrinking, what happens at the beginning is really important. So the updates we make at the beginning, which points happen to be selected, give us our starting point, and all the adjustments after that are just tweaks to the starting point. So it can take a long time to move away from the starting point. And so if we start with different set of points, we're gonna get different results. And so I've got all of these random points. So essentially, what I have here is I have 3 different lines. I have this line based on stochastic. I have that line based on stochastic, and then I have this line based on the non-stochastic gradient descent. And as I was making this video, I noticed one little formula problem that I fixed here. So I'm gonna have to retype this into Desmos. But over in Desmos, if we want to see what we had here, these purple and green lines are what we got using the stochastic gradient descent. So we can see the green line and the purple lines, we got slightly different results. The purple one seems to have worked out better. And I didn't change the method at all. It's just random luck, essentially. Right? But you can see the purple one is actually more evenly spaced between the red and the blue and has bigger margins, right? So purple is better than green. Right, and even though they're the same number of iterations, they're both 100 iterations. We get different results sometimes. If we sent them both to like 10,000, 100,000 iterations or something, then we would expect to see them getting more convergence. Right, so that's the thing is with the stochastic gradient descent, each step is quick in terms of calculation, in terms of computation time, but you want to do a lot of steps if you want to get convergence. With the non-stochastic one, we should get it going to a good spot quite a bit faster. So I also did only 100 steps. Now let me just tweak these numbers to reflect the fact that I fixed a formula problem. So this should be 0.3739, and then 0.20714, and then 0.19959. Yeah, those look good. And now I'm just going to fix my margin boundaries. And now we can compare. Now I'm going to compare to the purple one because the purple one was the better of the two for the stochastic. So for the stochastic, after 100 iterations, we did it twice, and this was the better result. For the non-stochastic, this is our result, and you can see it's even more evenly spaced. It's quite evenly spaced between the red and the blue, not perfect. And if we look at the margin boundaries, they're wider, quite a bit wider than the purple ones, right? So obviously we have more calculations at each step, but we get better results for the same number of steps, right? So if we want to do a fair comparison, we might want to compare this to, say, a stochastic gradient descent after a lot more steps, right? Because here we're calculating a lot more things. We're calculating 12 points each time for 100 steps. A more fair comparison might be to compare this one to a stochastic gradient descent after not 100 steps, but after 1200 steps. That would be a similar amount of calculations, right? And if we wanted to do that, we could go ahead and do that. We could go back into our book here, and we can just say, hey, let's copy and paste this down to like 1200. So what happens when we go all the way down? 1200. I probably need like 1200 and a few more rows just to get. Yeah, okay. Right, so after 1200 steps, we might get something like this, and you can see it's re-randomizing every time, right? So I can just get a couple of different results here, but the stochastic one after 1200 steps, we're getting negative 0.37 x minus 0.2111 y minus 0.2088 equals 0. And we can put our margin boundaries on that. And when we do that, let me just make these all the same color. So I'm going to make these green dotted. What do we see? Let's get rid of the purple one, right? Because the purple one was stochastic after only 100 steps. So if we're looking at the non-stochastic after 100 steps versus the stochastic after 1200 steps, you can see the results are really similar. The lines have slightly different slopes. They're a little bit different, but they're pretty close. The margin boundaries are about equally wide. The lines are at about the same spot. So you can see for the same amount of computation, you get about the same results, right? Which is pretty cool. So there we go. That was just showing you the non-stochastic version of gradient descent for this problem, where we use all the training points at each step. And with some data, this might be something you want to do. With other data, especially if you have large training sets, you really want to go with the stochastic gradient descent. And like I said in the lecture, there's a middle ground. You can always do a thing where at each step, you take a random sample of points, not just a single point, but maybe a random set of 10 points or something like that. And you can make your updates based on that. If we had a huge amount of points, you can imagine how we might have set up this sheet, right? This sheet here. You can see every time I go through this sheet, at every step, my x1, x2, and y are the same. But you can imagine if I just had some random number generation at each step, I could randomly select 12 points from a larger list and have a different have a different set of 12 points at each step, right? And so then we're getting some randomness, but also we're also getting the benefits of having a larger number of points. For instance, the first few points that we select in a stochastic gradient descent, if we're just selecting one point at a time, those first few points become really influential. If we sample 12 random points, then we can sort of dilute that influence over a larger set of our data. So there are some good advantages here. So you can sort of tweak these methods in a lot of different ways. If you look online, you'll see lots of different implementations of gradient descent involving sampling, involving just one point at a time, all these different things for different problems. And that's how you do it. And you probably wouldn't do it in Excel, right? Doing this one in Excel was kind of annoying. I would really, you'd have a better time doing this in Python or something. So that's it for this little bonus video. It went a bit longer than I thought. I actually talked a little bit more than I thought, but hopefully you learned something from it. Have a good one, and I'll see you next time.